Today, we'll deconstruct a problem from the 2005 AMC 10B. So, you let x and y be two-digit integers such that y is obtained by reversing the digits of x. X squared minus y squared equals to m squared for some positive integer m. So what is x plus y plus m? So this problem is essentially a system of constraints. So our first step here is not to guess, but to translate these words into a precise algebraic language. The most critical step here is to represent x and y. A two-digit number we can write as AB. So we know that we can represent all two-digit numbers here as A, B. Now notice here that AB is not A times B, but AB here is equal to 10A plus B. And this is the key to solving this problem. So we can let the digits of x be A and B. So we have x equals to 10A plus B. And the problem states that y is the reverse of x. So if you have x as AB, y will equal to BA. And BA would equal to 10B plus A. Now, if you don't get why AB is equal to 10A plus B, we'll realize that B here is the ones digit, so essentially B times 1. And then A here is a tenth digit, so it's going to be A times 10. And like this is in base 10 right now. So A must be between 1 and 9, and B must be between 0 and 9. B cannot be 0, otherwise y would not be a two-digit number, so B is also between 1 and 9 here. And now we substitute these representations into the given equation x squared minus y squared equals to m squared. This structure on the left, you can see x squared minus y squared is a difference of squares. This should always be the first thing that you should recognize. X squared minus y squared factors into x minus y by a difference of squares. This equals to x minus y times x plus y. So our equation will become x minus y times x plus y. This is equal to m squared. Let's calculate the terms x minus y and x plus y using our definitions. First, x minus y. X minus y here is equal to 10A plus B minus 10B plus A equals to 10A plus B minus 10A minus 10B minus A. So this is equal to 9A minus 9B. And we can factor out the 9 here, so it'll become 9 times A minus B. Next, x plus y. X plus y would equal to 10A plus B plus 10B plus A. And this will equal to 11A plus 11B. Factor out the 11. So 11 times A plus B. And now we can substitute these back into our factorial equation. Our equation is now 9 times a minus b times 11 times a plus b equals to m squared. We can combine the constants. So this equals to 99 times a minus b times a plus b. And this is the central point of the problem. We have an integer expression on the left that must equal a perfect square. So this is no longer just algebra, it's number theory. We can look at the prime factorization of 99. We know that 99 equals to 9 times 11. 9 is 3 squared, so this equals to 3 squared times 11 to the power of 1. So our equation is going to be 3 squared times 11 times a minus b times a plus b. For the entire left side to be a perfect square, every prime factor in its prime factorization must have an even power. So the 3 squared is already a perfect square. And the 11 to the power of 1 is the problem. It has an odd power. So this will mean that the term a minus b times a plus b must supply at least one more factor of 11 to make the power of 11 even. So therefore, a minus b times a plus b must be a multiple of 11. And now we can find the final constraints to solve for the digits. Since 11 is a prime number, we have either a minus b or a plus b must be a multiple of 11. We can analyze our variables a and b here. A and b we know are both single digits from 1 to 9. What is the possible range for a minus b? The maximum is going to be the max of a minus b is 9 minus 1 equals to 8. And then the minimum of a minus b would be the opposite. 1 minus 9 equals to negative 8. However, we know that a minus b can never be 11 or negative 11 from these two facts. So this term cannot be the source of the 11. Now, what is the possible range for a plus b? Well, we know that the minimum of a plus b is equal to 1 plus 1 equals to 2, while the maximum of a plus b is equal to 9 plus 9 equals to 18. There's only one multiple of 11 in this range, 11 itself. Therefore, we have a definitive conclusion, a plus b equals to 11. Now, our equation becomes 99 times a minus b times 11 equals to m squared. So we have 3 squared times 11 squared times a minus b equals to m squared. For this to be a perfect square, the remaining term a minus b must also be a perfect square. So let's list the possible perfect squares in the range of a minus b, which is 1 to 8. The only options are 1 and 4. So here we have two cases. The first case, a minus b equals to 1. So the first system would then be a plus b equals to 11, a minus b equals to 1. We can add the equations to cancel out b. So we have 2a equals to 12, a equals to 6. And b equals to 5. And then the second case is a minus b equals to 4. So we have a plus b equals to 11, a minus b equals to 4. Once again, we can add the two equations, canceling out the b. So we will have 2a equals to 15. A is going to be equal to 7.5, which is not an integer. So we have a equals to 7.5 here, and then b would equal to 3.5. And this case does not work because we want an integer, not a decimal. So this case is impossible. The only solution is a equals to 6, b equals to 5. And now we have found the digits. So we have to find x, y, and m. We know that x equals to ab, which equals to 65. And y equals to ba equals to 56. And then m squared equals to 99 times 1 times 11 equals to 1089. So m is the square root of 1089, which is 33. And now the objective was to find x plus y plus m. So we'll have that x plus y plus m equals to 65 plus 56 plus 33. And the answer would then be 154. And that is the solution to this problem. The problem looked complex, but it was deconstructed by translating the words into algebra, then factoring, and then applying basic principles of number theory. So this was the process to solve problem 24 on 2005 AMC 10B.